All right, so let's take a look at this warm-up where you're asked to determine the degree, the number of complex roots, and the number of real roots for each of these graphs. So remember, the degree could be thought of as the number of directions that any graph travels. That's a real simple way of thinking about it, but it can kind of be nice to give you a general idea of what's happening. So in this particular scenario, I'd say that this graph is going down, then up, then down again, then back up. So the degree should be 4. As we look at our real roots are always where the graph crosses the x-axis, which for this first graph would be twice in those two locations. So that's how the real roots would be 2. Now finally, when we're talking about complex roots, remember that those complex roots come from any spot where there is a parabola which opens away from the x-axis. So remember, if I were to zoom in, and I'm going to zoom in real close here, if I were to zoom in to this spot, this parabola does not touch the x-axis anywhere, and so therefore it has to have 2 complex roots. So that's why this ends up with 2. And you notice that in this scenario, 2 complex roots, 2 real roots adds up to a degree of 4. As we look at the number 2, let's start with the real roots. So I have 3 different x-intercepts, 1, 2, and 3, and so that would mean I have 3 real roots. And again, I have another spot where you have a parabola which opens away from the x-axis. And so that would be a set of complex roots. Because remember, your complex roots always come in pairs. They must always be in pairs. So this will always be an even amount for your complex roots. Right? So roots are in pairs here. And so let's take a look at that degree. And if I follow everything else, I have direction of 1, 2, 3, 4, 5, and so that is a degree of 5. I have 3 linear roots and 2 complex roots, which adds up to 5. So for this last example, we have a little bit more going on. Let's start again with the real roots. So here's 1 real root, here's a second real root, and so there are really only 2 real roots. And you might say, well, wait a minute, isn't this a double root because it bounces? And isn't this a triple root because it kind of looks like that? Well, yeah, that is correct, and that's important for us as we look at our degree. So we have 1, 2, 3, 4, 5, 6, 7 for our degree, and so that should add up to 7 for your total degree. And let's come back to that. We still have this spot here which has our 2 complex roots. And so there are 2 there because that is the only parabola which is opening away from the x-axis. These parabolas, or these parabola-type shapes that we see elsewhere, are all opening towards the x-axis, and that doesn't count. So every parabola that opens away from the x-axis gives you 2 complex roots. So as I look at this last example, it's kind of an interesting one. I only have 2 real roots, and I have 2 complex roots, but the degree is 7. So that is important that you're able to fill that out correctly, because this is a double root, that's a triple root, and so the amount of roots determines the degree. In these examples, you're asked to write an equation for the given roots in standard form. So this is given to me as x equals 2 and x equals negative 7. Those are 2 x-intercepts. My second example says there's a double root at x equals 5. That implies that all of these others that you're given are considered linear roots. So the quickest way to find that out would be to write your equation in factored form. So this would be x minus 2 from the root of 2, and then you'd have x plus 7 from the root of 7. And now to write it in standard form, you just need to multiply this out. So you multiply out your factors. You can use a generic rectangle if you need to, x minus 2 and x plus 7. So as you multiply out all the different parts of your generic rectangle, you'd end up with your standard form equation as y equals x squared plus 5x minus 14. Now if you had a double root, that means that your equation would be y equals x minus 5 quantity squared. That's what we've talked about, which if you needed a generic rectangle would be x minus 5 and another x minus 5. So when we multiply these out, this is where students make their mistakes, of course, that will always annoy your math teacher, that it should be y equals x squared minus 10x plus 25, because we still have students who are not squaring correctly and forgetting that negative 10x. So here you have your quadratic, and both of these are quadratic equations, and you have 2 real roots for each of these quadratic equations. Now this third example, I have 3 roots. These all happen to be linear roots, so as we write out our factored form of the equation, you'd have x minus 7, x minus 1, and x minus 3. And that, from what we've talked about already, would tell us that this is a cubic polynomial because I have 3 linear roots. So instead of being a quadratic as your final answer, we would expect a cubic. Now you are asked to put this into standard form, and this is not in standard form yet. This is still in factored form. So you need to turn it into standard form. And the way to do that is to pick any 2 factors. I'm just going to pick the first 2 because those are listed first, and I need you to multiply out as a generic rectangle. You could do that just quickly by knowing your pattern, or of course you could use your generic rectangle if you needed to be able to multiply and make sure you get all of the correct pieces. So x squared minus 7x minus 1x and plus 7. So right now our equation looks like y equals, what I just found is a quadratic from those 2, so I have x squared minus 8x plus 7, but then you still have this final factor of x minus 3. And so we still have some more work to do for these problems because this is still considered to be in factored form. I've multiplied 2 of the factors by each other, but I still have a third. And so what I'm going to do is I'm going to make another generic rectangle, this one a little bit larger, where you have 3 terms on the top, which is the x squared minus 8x minus 7, and you have the x minus 3 on the other side. And so now as you multiply, here's where your x cubed comes from, x squared times x, negative 3x squared. I'm multiplying all my pieces to get 24x, negative 8x squared, a positive 21, and a negative 7x. So now the standard form would be when you combine all your like terms from what we just multiplied out. So now my final answer would be y equals x cubed. I have negative 11x squared, a positive 17x, because 24 minus 7 is 17, and then a positive 21. And now we have the standard form for something that has 3 linear roots. So it's even better than writing this factored form. We can know how to multiply all this stuff out.